with Fil++ in MSO4SC, and then François Debré who is going to talk about the stakeholder part in the Hi-Fi magnet application. So I'll give an overview of Fil++. So what does it mean, Fil++? It means finite element embedded library or language in C++. It started in 2006 as a fork of Li5, which is a library which was developed by the group of Alfio Quarteroni and some partners. At the time, the idea was to rewrite the kernel, the mathematical kernel, and I wanted to have a tool to design, test, and reproduce numerical methods. Since then, this is still true. But there are many more features that I would like to have in Fil++. But Fil++ now is part of a big master plan, which is Fil++ is basically the flagship software of Semosis. What is Semosis? Semosis is a center of modeling and simulation in Strasbourg. It's hosted by the Laboratory of Mathematics. The core component is the modeling and control team, research team, and the master in scientific computing. This is a structure to promote multidisciplinary research and collaboration with enterprises. So at the national level, it's connected to the Agency for Mathematics and Enterprise Interactions. But we've created recently a network of MSO centers, modeling, simulation, and optimization, with similar structures as Semosis. Semosis is one of the two structures which historically were created in France in 2011 with Memosine and 2013 with Semosis. And now new ones are popping up in universities in France. So at the regional level, you have structures like Semosis, so Semosis in the east of France. And then at the national level, you have Amiens and this MSO network. And at the European level, you have EU MathSyn. So really, we would like to see this, hierarchical multi-scale graph. And for us, Fil++ plays a big role because this is our main way to communicate with the outside world. Of course, there are mathematics, but this is a way to deploy our mathematics in companies. So Fil++ has various features. One of them is its versatility. It provides a wide range of mathematical methods. From continuous Galerkin, discontinuous Galerkin, hybrid discontinuous Galerkin, reduced basis, fictitious domain, well, you name it. 1D to 3D, actually higher dimension would be also possible. There is also 0D. We can, of course, do 0D, but you saw some example yesterday. And yeah. It's also powerful in the sense that we can scale up to thousands of cores. We've tested up to, I think, 40,000 cores on Curie, on a Prace core. And we use PET-C, SLEP-C as our main workhorse. But we develop also our own in-house preconditioners, which allow us to scale on some specific applications. Yeah. But they are not like, here we have a nice framework where you can, it's very agile in the sense that it's easy to deploy PET-C on new applications, whereas for our in-house, they still need, they are research-based, so they still need to be, they still need some work in order to use them in all our applications. It's expressive in the sense that we provide a language for the developer of the applications to manipulate the Galerkin language. So you have all the mathematical concepts you need in order to write your code from meshes, function spaces, variational formulations, things like that. So it provides a high expressivity in the code when you work directly with the mathematical concepts. Well, here you have some kind of it's a little bit blurry, but you could see some keywords like integrate and meshes, function space, things like that. Well, we provide that. There are many examples on the web. And it provides also toolboxes. So the idea is to merge or to have ways to deploy very easily applications. Monophysics, of course, with so the main ones are CFD, computational fluid dynamics, computational solid mechanics, heat transfer. Then you can couple there. New ones are being built. We have also multiphysics, FSI, in our fluid structure interaction. In our context, FSI is used, for example, with fluid structure interaction for blood flows. So it requires relatively advanced algorithm for fluid structure interaction in that context. So we have quite advanced methods in order to deal with this. Heat and fluids. Of course, we do passive scalar simulation with fluids, but here we'll have the coupling typically with heat transfer and fluid, which is a tad more complicated. And applications like in thermoelectric, we have quite a bit of them. You saw the one from Lotfi yesterday. There is also Christophe. So we have quite a few of them. Here you see the Peltier module. So we have we can handle this kind of model. So what is a toolbox? It's basically an executable, and each application, an application is actually a directory with a set of files. These files are a JSON file. There could be one or more, depending on the number of physics you are dealing with. JSON is a data exchange format, which is less verbose than XML. It's heavily used by all this, Web 2.0 application services. We find it nice. Lorenzo showed you some example yesterday evening. We have some configuration files which are command line options. There is a strong link, of course, between the two. It allows for flexible changes of options when we run the application. The CAD geometry, eventually the computational meshes if they are not too heavy, otherwise we regenerate them on the fly, partition or not, and possibly some input data for the simulation, like with AngioTK I showed you yesterday, like MRI images. As I said, there are various numerical methods which are available. The language that we provide, the Galerkin language that we provide is, now it's not really about Phil++, it's more about the mathematical language. We try to have a very tight, let's say, like one-to-one mapping between the mathematical concept and what we provide in Phil++, so that the mathematician can actually develop his own, design his own numerical method. So it's a way for us to create new numerical methods, and we have been publishing articles with new kinds of methods. For example, here in fictitious domain, we propose it was proposed by other people, colleagues of mine, and then we further developed the methodology in fictitious domain methods called the fat boundary method. We developed the reduced basis method for nonlinear problems. Some level set methods also interesting. You've seen the hybrid discontinuous Galerkin. We proposed also some extension here, not as developed as what we have done for other methodologies. So the idea is that we have a kernel, we have various projects, we have teaching, because the idea is also that students are going to use Phil++, researchers are going to use Phil++, companies, people from other disciplines can use it. But the problem here is that, and that's where the language plays a tremendous role, is that in all the software, the difficulty is that you have several complexities colliding. You have the physics complexity, you have the numerical method complexity, you have the computer science complexity, and you have the algebraic solver complexity. If you consider computer science and algebraic complexity, they require high performance computing. You need to be very efficient. You need to be close to the machine and get, lots of power. But for numerical methods and physics, you would need actually more expressivity. You need to be flexible in the way that you present these objects to the user. And so in order to be able to tackle this, the Galerkin language, the language we developed in C++, allows us to translate from this either the physical toolboxes or the mathematical language we've implemented. We provide a kind of translator to the lower part of these graphics, to the algebraic solver and the computer science parts. That is to say that the user is not going to see the parallel computing part, is not going to see the algebraic solver part. Well, he needs to know a little bit about them, but it should be as hidden as possible. The partners, a lot of academic partners. So I actually have added SZE. Lotfi is using C++ quite a bit from what I've heard, and also with his students, so I'm very happy about that. We have a few universities in France and research centers, and also universities abroad. Regarding companies, so we have various projects. Some have ended, others are still ongoing with companies. You've seen some of these projects in MSO4SC. You have I2Brain here and IFI Magnet and VivaBrain here. Some other projects include, for example, blood rheology. So in this scale, we really look at the micro scale and really we simulate red blood cells. And we work with physicists who are interested in developing a kind of blood constitutive law and to allow being able to detect sickness in the blood in, let's say, with more rapidly than now. Currently, it takes time to detect that. You take a blood sample, then it may take a few days to weeks in order to get the results. And the idea is that with just a rheometer, you would be able to detect those illness. Metaflow is related to this one. The idea is to understand the impact of hemodynamics on the localization of the attachment site of tumor cells in the vascular system. It's actually interesting here. We work with zebrafish in order to do the real experiments, and we reproduce in silico, and we use actually AngioTK in order to do this simulation. And then there is a diffuse optical tomography application where we provide the software associated to a tomograph developed in Strasbourg. With companies, we have a few of them. MSO4SC plays a very important role for us because it's kind of the meta project, because it should allow us, by the end of the project, to be able to deploy the application that we develop with these companies, to deploy the services in the cloud and to provide services to companies. This is our strategy. This is extremely important that the project succeeds in this area so that we can actually provide services by the end of the project through MSO4SC tools. Plastic Omnium couldn't come, but they are extremely interested in the project, in providing tools in the cloud. They do scale 1 flows around cars, so turbulent flows, and we have been developing with them advanced post-processing tools on very large data sets, hundreds of millions of cells, and the size of the data set is like terabytes for one simulation, about a terabyte. And lastly, we have a technology that we've developed. It's called 4SC. So what you see here, it could be like also for MSO4SC with ParaView Web. So here you have ParaView. You have a plugin here that we've developed. You have the visualization here, it's an apartment. And then you have some parameters here. So you have the heaters. You have materials for parameters for the walls, for external walls, for the walls here. You have the external temperature. And you would like to have a 3D map of the temperature inside the building. And you want to vary these parameters. So you vary these parameters, and then maybe you use MSO4SC, and you launch the simulation. You wait for a few minutes, and then you get the result. Except that here, when you vary the parameters, the simulation is done real time. The simulation is done real time. So we use here the reduced basis methodology in order to do real-time simulation. You modify the parameter, and poof, a new computation is done in matters of milliseconds or fractions of milliseconds. Here, this is actually a hi-fi magnet application, non-linear, where we have also real-time response, and it's integrated into ParaView. It allows for engineers to do their studies. And now I don't know how to go to the next slide. So what's the web ecosystem? So you have the website. You have GitHub, of course. It's open source. We use Gitter in order to communicate. We have various forums. We use it also for MSO4SC. So if you don't have yet a Gitter account or GitHub account, you can create it and join us on Gitter. There are various people here already connected. Then we have the Docker cloud, so you can retrieve actually our Docker images in order to play with Fil++. We have the publication if you are interested in the mathematics that we do. Twitter and of course YouTube, we have a lot of videos, so most of the videos you see here are already on YouTube. So this is the abstract framework that we have. So Fil++ is here, you have GitHub here. So we do development, it's hosted by GitHub. And on GitHub we have various projects using Fil++. And we have various collaborators, companies who are contributing to the project. For each project, for Fil++ and the sub-projects, we have continuous integration. So especially with BuildKite. So BuildKite builds all our projects, and Travis is doing continuous integration for Fil++. And if everything goes right, then there is automatic deployment on Docker Cloud, and hopefully we'll do the same very soon with Singularity for MSO4SC, and yeah. So who's working on the MSO4SC project? So you've seen Giovanna yesterday. There is Marcella, she couldn't come. Vincent is a new father, so he's like stuck in Strasbourg for yet a few more months. Guillaume over there, this guy is Lorenzo, so he's hiding in, he's a ski specialist. And Christophe and myself, a new person will join us in September on the Eye2Brain application. So what we have been doing, well, this is rough. I mean, I didn't go into the details, but thanks to MSO4SC, we have now book.philpp.org, where we use a combination of ASCII doc, which is a very powerful language text. This is text for technical writing. And we have been, as I mentioned 2 days ago, we have been developing the same kind of tool for MSO4SC and IFI Magnet in order to deploy our technical documentation. It's very easy to embed code, very easy to embed mathematical formulas into the system. So everything is available, open, and you can see how it works. It's extremely nice. And already in GitHub, you can actually navigate in the book through the link. So it's from my point of view, this is the almost perfect tool I always wanted for technical writing. We have been, of course, there is a singularity work, but we have also, thanks to MSO4SC, greatly improved the Dockerization of the system. We have been porting, of course, C++ on the FT2. And there are various things coming with HDG framework and toolboxes that will be presented at ENUMAC, which is a big conference at the end of September. So we should not organize something at the end of September for MSO4SC. I would be in trouble coming. On reduced basis, we have also a big update coming. Turbulence modeling, but HANS models. We have a level set framework and toolbox system, which is coming now. It needs to be merged into, so it's like what Edgear presented. We use this branching and pull request system in order to manage contribution. We have a Maxwell toolbox coming and hopefully better documentation. This is a workflow we are considering in the future. Thank you.